As I was telling you, folks, these lectures are recorded and I post them on YouTube. And today we said that we are going to go and review some other things that you learned in college algebra. Now, per my promise, I'm going to go over some questions that are from the book, from the homework, and do reflect the topic that we will discuss today in very good detail. So, for example, and this is a question from section 1.3, but we are going to use the same technique in section 1.4. This is question number 5 of section 1.3. And this question is on page 43 in your textbook. And you get a graph there, and the graph looks something like this. And I'm going to sketch it here, and then you'll see that we'll do something interesting with this graph. So it goes from 1 to essentially 2 over here. So it goes to high 2. This is the the grid in the XY plane. This would be 1 over here, and this would be 1 over here, and this would be 2. The grid that goes through these points, something like that. So I'll show you in a second why we need to do this, and we need to be a little careful here. I go 1, 2, 3, 4 units to the right and 1 unit down. So 1, 2, 3, 4. And if I go 1 down, now I get this one, and I go like this. There we go. That's another part of the graph. And then I go 2 more units to the right, and I connect with 0 here. All right, folks. So these are the numbers 2, 3, 4, 5 here, 6, and that's about it. All right. So this is the graph that we are looking for, and it says here, use this graph to describe the graphs of the following function. So this would be the graph of a function y equals f of x. This one here, that's pictured on my screen. And you're looking to, folks, let me 1 second because I don't know if the recording is still working. Oh, yeah, it is. Okay, so just check the recording. The camera seemed to turn off here. All right, so this is the graph of a function y equals f of x, and you would want to do something like you want to graph this one, y equals f of 2x. What happens with that? Or b, y equals f of 1/2 x. What happens with that? So when you so basically you see here that we're increasing what we called last time, we called the angular velocity, the coefficient of when you say cosine x and the versus cosine of 2x. So we go faster, twice as fast. What happens with the graph? And we learned that when we describe sine and cosine, and if you look at the overall picture, folks, this really looks kind of like the graph of, if you want, the graph of sine or the graph of cosine, except that instead of having that wavy shape, it has a bunch of segments going up and down. But the idea is sort of the same. So we're going at a faster speed. What's going to happen? Well, so the repetition, the pattern that we see here will repeat twice as fast. However, you don't have to memorize those things because I'm going to teach you today how to do this problem using technology. And the reason why I'm doing this is because this is a good review of notions like slopes and intercepts and line equations and things like that, things that we said that we would review before we move on to calculus because they're really important. They're actually the key thing for calculus. So what I'm going to do, folks, I'm going to teach you how to, or probably some of you know already, how to implement, how to do this graph in Desmos. So let's take a look at this carefully here. You also have it in your book, so I recommend that you keep your books next to you. Again, open at page 43 so you can actually look at that graph, because what I'm going to do, I'm going to represent this graph in Desmos. So what's the trick for Desmos? The trick for Desmos is to remember these points, these corners here, and to actually calculate equations. There's a slightly easier way, but I'm going this route of calculating equations of lines in order, excuse me, in order to review those equations. So before we pull Desmos on the screen and we do the work with Desmos, let's do the prep work here on the whiteboard. So first of all, the first line segment here is this one, connecting the points 0, comma 1 really is this point here to the point over here at the top is the point 1, comma 2. So if we have a line connecting, so the line connecting the point 0, 1 to 1, comma 2, what is the equation of this line? I want to figure that out first. Well, I have to find the slope. Remember that in order to find the equation of a line, you have to find the slope. And the slope formula is y2 minus y1 divided by x2 minus x1. So in my case, will be the difference of these two, 2 minus 1, divided by, and then the difference of these other two, the x components, the first entry is divided by 1 minus 0. Now make sure that you do that consistently. In other words, if you start with the second entry of the second point, then make sure that you also start for the denominator here, you start with the first entry of the second point. So if you do 2 minus 1, then you have to, so this one minus this one, you also do 1 minus 0. Otherwise, you get the wrong slope and the wrong calculation. All right, so that being said, this turns out to be 1, as you can easily see. 2 minus 1 over 1. So the slope is 1, and we already know the y-intercept to be 1 here because this point is already on the y-axis. So this line would have equation y equals x, 1 times x plus 1. So this is the equation of the line. Now remember that this is the formula for x between 0 and 1. So we're going to say here 0 less than or equal to x less than or equal to 1. Remember that we draw piecewise defined functions. So we need to make sure that we understand on which interval that formula is valid. All right. So that being said, let's move on to the next thing, which is the second line here, connecting 1, 2 to this point here, which is 4, comma, negative 1, the one at the bottom. So the second line, the line connecting the point 1, comma 2 to 4, comma, negative 1 will have a slope of, and we write here the slope, and the slope would be by the exact same type of calculation. So we're going to start with the second, negative 1, folks, minus 2 divided by 4 minus 1, and that's going to turn out to be, as you can see here, let's see, negative 1 minus 2 is negative 3, folks, and 4 minus 1 is 3, so this is going to end up being negative 1. This is a slope of negative 1 for this particular function. Now, this turned out to be nice, a nice calculation, but in practice, you might run into some uglier numbers. So don't be afraid of those because, slope rarely turns out to be an integer like it turns out to be in this case. All right, so that's the slope, but then the question is, how do we find the y-intercept of this line? Well, it's not so easy. I mean, you can proceed on the graph here. You can actually see that it's at 3, but I'm going to show you a more algorithmic approach if you want. So we can write the line equation as y equals mx plus b. Remember, that's the equation of a line. In this case, negative 1 times x plus b. And we don't know what b is for the moment, but we are going to find it by realizing that this line goes, for instance, through the point 1 comma 2. So that tells me that when y is 2, x is 1. So we get 2 equals -1 plus b. And if we solve for b here, we will figure out that b has got to be 3. So the equation of a line is y equals -x plus 3, where the numbers x is between 1 less than or equal to x less than or equal to 4. So this is the second equation of a second segment on the graph. And I have one more, but I don't have much room to write on this page. So I'm going to move a page and I'm going to calculate there. Just remember that this second segment, the last segment here, connects 4, -1 to 6, 0. So the segment connecting 4, -1 to 6, 0, or the line segment, let's say the line segment here, so it's part of a line, obviously, we'll have a similar equation. Slope will be done, and I'm going to say quickly here, so please calculate the slope for me and tell me what it is in the chat section for this particular one. If you understood what happened up to this point with the other lines, then you shouldn't have a hard time to figure out this slope. So I'll wait for you folks to tell me in the chat what the slope turns out to be here. Let's see, did anybody calculate that? Or you can open your mic and tell me, yeah, so let's see. So there's a couple of people. All right, 1/2. So you got 0. Good job, folks. Amber and Sam. And I'm pretty sure there's a few other people there. 0 minus -1 turns out to be 1. And 6 minus 4 turns out to be 2. So indeed, the slope is 1/2. So we got the slope to be 1/2. Let's write the equation. The equation is y equals 1/2 x plus b, right? And we know that this line goes through the point. I'll take the first point here. It doesn't really matter. You'll get the same result if you take the second point, but this line goes through a point 4, -1, which means when y is -1, x is 4. So -1 is 1/2 times 4. So due to this point here, right? Plus b, and you can calculate easily here. This is the same as saying that -1 is 2 plus b. So b has got to be -3 apparently. Yeah. All right. So b has got to be -3, and the equation is y equals 1/2 x minus 3 for x, the x between 4 and 6. All right, this is everything we need to do in order to solve the problem, because with these things here on my screen, I'm going to open up Desmos, which I didn't show you yet. So let me stop sharing this whiteboard. So I'll stop sharing the whiteboard, folks. Okay, let's see, what is the share button? It went away from my screen. 1 second. Where's the share button? All right, folks. Sorry about that. Not that. All right. Huh. Now that is funny. Okay, I'll close the whiteboard. Okay, oh, there we go. There's my share button. I lost my share button. Sorry about that. Okay, and I go to this nice screen of a football player. What's this guy's name? Falcon, Freddy Falcon or something. All right, so I'm gonna do a share of this page, and as I said, we go to Desmos. Got to open up desmos.com. Okay, and a graphing calculator, and we are going to graph that particular function. Now remember what the equations were, because I'm going to typeset directly the formula. So I'm going to say f of x equals And I'm going to put curly braces here. And I'm going to say when 0 less than or equal to x less than or equal to 1, we figured out that the equation was y equals x plus 1. So I'll put colon, and then the formula was x plus 1. Then we got that, you can easily see that we get this on the graph. Then I'll say comma, and then the second formula, when 1 less than or equal to x less than or equal to 4, we got the formula to be x negative x, y was, so the equation was y equals negative x plus 3, right? Okay, and we got that. Then we go, that's the second formula. You see, it reproduces exactly the thing that we would have in the book. Comma, and finally the last formula for less than or equal to x, less than or equal to 6. And the formula, colon, the formula is, we found 1/2 x. You want to get out of here with an arrow, and 1/2 x. What do we have? Minus 3? Yeah. Minus 3. So we got this particular graph, and you can see here, this is our own function. All right, and now the rest of it is, a piece of cake. So answering those questions in the book now, you can easily see that f of 2x, for example, that's part A. Oops, I wrote the wrong thing. F of 2x is that, so you see that the pattern, this exact same pattern is repeating twice as fast. So you go one time like that, and then you go another time like that if you were to repeat this pattern. So it's basically shrinking the initial graph because it's going twice as fast. That's f of 2x. If you do f of 1/2 x, you will see that the exact same pattern is now stretched because we go twice as slow. So, oops, take that out of here. There we go. And then you have, that's part B, part C, f of negative x, you guess what will happen. So this will be flipped over. So f of negative x is here. I'm sorry, negative, was it? Oh, sorry about that. F of negative x, it gets flipped over around the y-axis. It's negative x. I was looking at negative f of x. All right, so this gets flipped over. So x, this is the red graph, the initial graph. X changes to negative x, so 4 to negative 4, 6 to negative 6, and so on. So that's why it flips over on the other side of the y-axis. And finally, negative f of negative x, that's what the one I was looking at, it will flip over, so around the x-axis, it will flip over the graph of f of negative x, the purple one that we have here, it will flip over around the x-axis. So negative f of negative x, there we go. So that's the one above, flipped. All right, so this is how we do this problem. Again, in the book, it doesn't say to use decimals, but I strongly recommend that you use decimals, but know what to do in decimals. Again, know how to calculate slopes so you can represent the function properly and understand how to get the solution. So these are the graphs that would be required for problem 5. All right, do you folks have any questions here before we move on to something else? So I'm going to stop sharing decimals, and we'll move on to the, we'll go back to the whiteboard. Any questions here, let me know. All right, then I'll stop sharing decimals. And this was more or less, if you want a review for lines, equations of lines, slopes, and things like that. If you need a more in-depth review, maybe this was good enough, but if you need a more in-depth review, then do let me know, and we can work on that. Or you can take your pre-calculus or college algebra books, and you can look there, and this is topic that's discussed there. So this is a really important thing. Without this, I wouldn't be able to move on because our next lesson really focuses on a geometric problem, the problem of drawing tangents to a graph. And you certainly need to know how to do equations of lines there. All right, so we are going to start today lesson 1.4. I'm gonna change pages here. So I'll go here. I'm sharing with you this whiteboard here, folks. And lesson 1.4 is the title of that is the tangent and velocity problems. All right, so this really is about figuring out the tangent to the graph of a function. And I will tell you that this is a very old problem. And this has been around for many years, as in thousands of years. The intention to calculate the tangent to a certain type of curve. And people had a good intuition. What would be a tangent? Say, so if I draw a circle, what would be a tangent to a circle? Well, that would be a line, and in this case, the correct definition would be a line that intersects the circle at exactly 1 point. Something like that would be called tangent. And if you look at all the possible situations, this is the unique way to make sure that a line intersects the circle at 1 point, because if you draw another line, it's either going to miss the circle like that, or it's going to intersect the circle like that. So at 2 points. So the only way to draw a tangent would be to really intersect the circle at exactly 1 point. Now, with circles, it's a little easier than it would be with, let's say, parabolas. And why would parabolas be important? Well, they would be important because, as we said in physics, an object moving out in space is governed by gravity, essentially, unless we have an engine that pushes the object over and over. So if you throw a rock or you shoot a bullet or something like that, or a missile or something, everything is going to be eventually once they leave the the initial propeller, they are governed by gravity. So gravity pulls the object down. It has an initial velocity, but it follows a parabola. So when an object follows something, a trajectory like that, like a parabola or some other types of trajectories, it's very important to calculate its velocity. And velocity in physics was determined that would be in the direction of a tangent to the trajectory. So why would that be? Well, intuitively, think of it this way. Let's say we move a pendulum, and this is a pendulum over here, and it moves, now a pendulum moves along a circle, right? So it moves up and down, back and forth like this. Is an oscillating move. But then let's say at some point we cut off this wire, the string connecting the pendulum to the object, to the top of the ceiling or something. And then when we cut this off, if you look at the trajectory, so let's say the pendulum was going down like this, and at some point here it detaches. Well, when it detaches, it's going to follow a tangent trajectory, so it's going to go like this for a while. Whatever the point was, the initial point was when we cut off the string. And then it goes like this along the tangent to the trajectory, and then, it's going to fall down. But for a while, it's going to go along the tangent. So that's kind of the idea. That's why these tangents would be important. And as I told you, the most important problem would be that for a parabola, Because so if we understand this parabola at the usual parabola y equals x squared, then every other parabola we sort of learned in the previous lesson, or we learned in pre-calculus, or whenever you took college algebra and trigonometry, that every other parabola can be essentially obtained from this one by shifting it around, moving up, moving right, moving left, and things like that, pushing it all over the plane, and you get every other parabola that opens up and down. And if you want to, if you accept that the correct move would be to actually rotate the parabola, then you can rotate parabolas and you can position them anywhere you want in the plane. All right, so if we understand how to draw tangents to one parabola, it's kind of like you do with a circle, right? You understand how to draw tangents to one circle, and you know how to do for every circle. Well, that's the same story for the parabola. So we want to draw a tangent line to the parabola. But guess what? The definition that we had for the tangent line as the unique line that intersects the parabola at one point, it's not going to work here because for a parabola, there's a lot of lines that intersect the parabola at exactly one point. For example, if I draw what we can call intuitively tangent here, this one, that would work. But there's also lines like this one here, that is not going to intersect the parabola again at any other point. So the definition of having a line that intersects a parabola at just one point is not correct, is not accurate. So how do we define then the tangent to a parabola? Well, that is a tricky question. And guess what? It took humanity, the humanity as in like everybody on earth here, it took humanity a lot of years to think about it. Thousands of years people weren't able to figure out how to do this parabola tangent thing properly. Until Isaac Newton, the other famous physicist, figured out a clever way of doing things, and then after that, calculus. We can say that calculus was essentially born. So we're looking at stuff that was discovered relatively recently compared to to how old a subject mathematics is. For instance, geometry. Everybody knew about circles and parabolas too for a long time, thousands of years ago, maybe more than 3,000 years ago. There's documents that people knew about circles and tangents and stuff, and parabolas and hyperbolas and such. But what they didn't know of a rigorous approach to the tangent problem for parabolas. So it's a relatively recent thing. If we accept that relatively recent means within the last 500 years. So here's what Newton's brilliant idea was to figure out this thing with a parabola. So he said, I'm just going to take the parabola here. I'm going to change the page here, and I'm going to take a point somewhere here on the parabola. And in fact, I don't like the picture that I made here. So let me make another picture. Let's exaggerate the parabola, kind of something like this. This is not quite a parabola, but I'll exaggerate the picture just to see what's going on. So remember that we really want this particular line that goes like that. It follows my mouse, so it touches at one point, but it doesn't sort of go inside. It stays on the outside of a parabola. Now, what's the outside of a parabola? Intuitively would be this place here under the parabola here. That would be the outside, and we can call the inside this one here. But obviously, this is not an inside because it's open at the top. So these notions are relative. All right, so here's the deal. One approach to finding the tangent, Newton said, was to start by first drawing secant lines. So Newton said, let's fix a point here. Let's say this is the point 1, 1, which is on the parabola. Remember that the parabola has the one we're looking at has equation y equals x squared. And if we say, sorry about that, folks, I don't intend to scribble here, but it's a little harder on the tablet. So, so if I say, folks, if I say the point 1 comma 1 is on the parabola, you probably agree with that because when x is 1, y is 1. So there we go, we're on the parabola. So if I say, okay, let's connect these 2 points here. And this other point here is at a point, let's say x comma x squared, where x is, you know, some other point relatively close to 1, right? But not 1, not 1. So this is a different point on the parabola. Now what happens here? So I want to let this point slide down. So that was Newton's brilliant idea. I want to let the second point slide down towards the first one. Then what happens there? Well, this particular line will slide down towards what I would be able to call the tangent. So, so this particular line will go down a little bit and will slide down towards, you know, this, and this would be the correct notion of tangent. Of course, you can define some other notions of tangents, and there's a subject which has to do with calculus. It's called convex geometry, where you would describe a tangent line as the result, as the supporting line for a half plane enclosing this that containing the entire parabola. So that's a slightly different approach, but it boils down to eventually getting the same result. So so let's focus on Newton's method. So again, the idea of sliding one of the points of the secant line towards the other, that was a brilliant idea. That was the main germ, the one that started calculus in the form we know it today. And now let's see what happens with a line here. So the line here, this line connecting x comma x squared and 1 comma 1 will have a slope. What is the slope of that line? So the slope of that line will be the difference of y's, which is that's why I did the slopes earlier to review this thing, x squared and 1. So we subtract x squared minus 1. All right, divided by the difference of x's, which is x minus 1. By the way, folks, those of you who will eventually take physics and stuff like that, in physics, this is, they like to write things like this, delta y divided by delta x. So displacement in the y direction minus displacement over the displacement in the x direction. So that's what you will see in physics. It's the same as our slope. So that's how they like to calculate slopes in physics and the notation there. If you don't take physics, don't worry about that. All right, so this can be calculated. This quotient here can be calculated, and the point is in this particular case, it can be calculated easily by doing a little bit of algebra. Now, does anybody remember? So if I write x squared minus 1 over x minus 1, anybody remember how to factor x squared minus 1? Can somebody write me in the text there? So let's see if we remember that from college algebra again. We learned how to factor x squared minus 1. So when you factor trinomials, now this one doesn't have an x in the middle, but it's kind of the same idea. So anybody remember, folks, factoring x squared minus 1? Let's see. I'll wait for you to write me in the chat. All right, so again, the question is to factor x squared minus 1. I'll send the question in the chat. All right, there's a couple of people here. All right, so yeah, both of you are right. So both Liam and Nathan are right. So it's the product x minus 1 times x plus 1. Very good. So it's good you remember that. Now, folks, if you didn't remember that, please brush up those simple factorization problems. Again, this is since this is a review section, essentially brush up on those, you know, factoring trinomials and things like that, because that's important, really important in this class. there's no way to do well in this class without those. So we can write here, for instance, x plus 1, x minus 1. All right, so when we write that and we write that over x minus 1, we can see that something cancels here. And fortunately, this troublemaker of x minus 1 cancels out, and we really end up with x plus 1. All right, so we are able to figure out, folks, we are able to figure out the quotient here, the slope of this line. This is, remember, this is the secant line. But now I can say here at the limit, as x is very, very close to 1, I'm going to say x arrow 1. So x is very, very close to 1. This number x plus 1 gets very, very close to 1 plus 1, right? So so would be close to 2. And that turns out to be, folks, the real slope. That turns out to be the slope of a tangent line. And once I have a slope of a tangent line, which is going to be this one here, once I have a slope of a tangent line and I know that the tangent line goes through the point 1, comma 1, all right, so remember the equation of a tangent line is going to be the slope, which we just found to be 2 plus b, some y-intercept b, and we can find the y-intercept by asking that the line goes through the point 1, comma 1, because it's the tangent line at the point 1, comma 1. So 1 will be equal to 2 times 1 plus b, and b will end up being -1. So let's see that, let's see on a graph with decimals that indeed y equals 2x plus, minus, I just said, come on, minus 1. Let's see that that is indeed the tangent line to our parabola. So, so let's stop sharing this thing here and let's go to the other screen where we had Desmos. We're going to go to Desmos and we're going to ask Desmos to help us. I'm going to erase everything, delete everything that was here. So let's say another function, f of x equals x squared. We said that's our parabola, and we want to zoom in a little bit here because I want to show, okay, there we go, it shows 1. Let's plot the point 1, comma 1. I just zoomed in a little bit so I can, all right, so we plot the point, and the point is here, and we said that the line y equals, what we said, 2x, right, plus 1, was it plus 1 or minus? No, minus 1, okay, minus 1. All right, 2x minus 1, we found that line to be the tangent, and indeed, look at this, it's beautiful, it's indeed the perfect tangent to the graph. So this is correctly the intuition that we get from Newton. And I'm gonna do here a bit of an experiment here if you want. So so you can, oops, I clicked on the wrong button. I don't need to click on this burger here. So oops. All right, so so I'm gonna do a little bit of an experiment. So let's say let's plot another point, and well, you know what? Hang on a second. I'll show you something else. So let's do this to speed things up a little bit, so we can do something else as well. I'll do something in a different type of software called GeoGebra, because that allows me to do things a little quicker than Desmos. Desmos will be the main go-to program, but there's another one called GeoGebra.org, and it's okay. I'm going to leave this thing. And that is also a useful tool. There, by the way, both of these are free, so don't pay any money. If they ask you to pay money or something, this is all free here. And I'm going to say the GeoGebra Classic, for example, and that's going to pull here on the screen. I'm sharing a screen. Okay, so let's do the same thing. So it works more or less in the same ways that Desmos works, but it's got some advantages over that. I'll show you in a second why. So y equals x squared is here, and I hope everybody can see this. And I'm going to plot again the point 1, comma 1. There we go, 1, comma 1. Let's plot that. It appears on the screen here. Here. All right. And you know what? I don't want to see this point A here. So let's not show the label. And over here, I want to do the tangent. But the tangent we just figured out was y equals 2x minus 1. And that's the tangent right there. And what I want to do here, oops, let's zoom in a little bit here. What I want to do, which is slightly different, it's easier to do than in the previous program, you can actually choose a slider. What is this slider going to do? So I'm going to choose a slider. I'm going to put the slider here, and I'm going to say, let's call this slider, it's calling it A. That's fine. Let's call it A. So, so that allows me to give some values to this number A, and make the slider slide really. So, so it's going to go up and down and up, left and right on the screen. And if we plot the point, folks, A comma f of A on the screen. Of course, right now this point, oops, let me get rid of this stuff here. This point is going to be over here. So you can see that as you let the slider slide, your point will also slide. Oops, 5 is far away. It's up here far away somewhere. Sorry about that. There we go. There's my point. So let's show the point. It slides. Oh, there we go. There's B. So so B slides up and down around the graph. And I don't need to make it this big, so let's actually make the interval for B. Let's make it -3 to 3 or something like that, because I don't need to go that far. All right, so so let's do that, and then oops, oh, okay, do something else. Delete that. All right, so let's do that. Oops, I don't want that. Okay, I don't know what's doing here. So anyway, I have the f of A over here. I can leave it 5 and -5. It's not so important right now. Keeps asking me to make more sliders. All right. So let's do a slider on the screen. Okay, I'm gonna click on this slider. Okay, so I'm gonna go to settings. There we go. So so it gives me this option here. And I want to do the slide. Okay, I don't want to do it from -5. I want to do it from negative, let's say -2 to so that I have the point on my screen all the time. There we go. So we did that, and when we do this, you can see how the point, when you move a slider, your point moves up and down. And finally, let's do the point. Let's do the line connecting these 2 points. So the secant line. Initially, the secant line, you can see that I can move this point on the graph as I want. The secant line can be drawn with this line by just simply connecting these 2. And I can make this line, I can color this line with, I can color it with some other color, let's say red. All right, and you can see how when I move it, and there we go. There's my line. There's my line. So so it goes really close to the tangent. And as you get close to that point, I don't want to show this B here. Now, why is B showing on the screen? Okay. All right. Oops. Okay, so let's move it on the screen. I don't want to show that letter B, so let's show label. All right, there we go. So now, as you can see, folks, as I am getting closer and closer with my point from either direction, with my point very close to 1 comma 1, I am going closer and closer to the tangent line. So that was Newton's brilliant idea, to use slopes like this, and then your secant lines will get very close to the tangent line. And as you could see, so from this little experiment that we designed here, it's very important, I stopped sharing, it's very important to have those slopes calculated properly. So that is really the first basic and the most important idea of calculus. And I don't think I have much time to cover a computational example from lesson 1.4. So I'll leave it at that. We're right where we need to be with the material. So what I invite you to do is, again, for these remaining days before Monday, please review everything that we did so far. So review how to define functions, how to use compositions of functions, how to graph them, how to use slopes to calculate slopes, and also factorization of trinomials. So this introduction that we review, if you want, that we have covered up to this point, is really meant to walk you through the main topics of pre-calculus, if you want, so that we're all on the same common denominator. And when we move forward with the material and we discuss about concepts of calculus, we all have these in our bag of tools, and we can use them whenever we need to. All right, so please review those if you need to. If you already know them, you don't have much to do. And I will hear from you folks on Monday when we really get into the new stuff, and that's really where calculus starts. So essentially, I have nothing to tell you today, folks. I'm going to stop the recording so